Hi, मैं हूं Mr. Sohen Chutke and I've helped over hundreds of children to achieve their dream result in the past 12 years. And today I'm going to conduct a session on haloalkanes. This is, by the way, the part 2 of haloalkanes. If you've not watched the part 1, you can go back and watch that particular part. So this is the second video of the haloalkane series. So let us begin with the second part of haloalkanes, wherein we are going to have a look in detail, in depth, a view of preparation of haloalkanes. So we're going to focus on preparation. Now there are few distinct methods for preparation of haloalkanes. Let's see one by one which are they. So we can convert haloalkanes, or we can convert alcohols to haloalkanes. So I'll be using alcohols. So from alcohols we can convert it to haloalkane by using, so I can write from over here. So by starting from alcohols and by using HX with them, or by using SOCl2, that's also known as the Darjan's process, and then by using PCl3 and by using PCl5. So these are the four methods. When I start with the alcohols, I can convert that to haloalkanes. Okay, let's see one by one. These are short methods, easier ones. Okay, so by using HX, now let me start with the standard alcohol, that is ethanol, also called as ethyl alcohol in common names. Okay, so this is ethanol and I'm treating it with HX. Okay, HX can be HBr, HCl, HI, HF. Okay, you know that X stands for halogens. Halogens is group 17. Group 17 is females carry bags in ATM. That's how I remember group 17 elements. Okay, and just leave astatine aside because astatine is radioactive, and if you form hydrides of the others, so we have HF, HBr, then HCl and HI. So out of these, which one will you prefer? Which one will you prefer to use? We will prefer to use HBr, or we can also prefer to use HI, because HI will dissociate with the most ease. Okay, the dissociation of HI is the most easiest as compared to HBr, then HCl, and then finally HF. HF will be the most difficult to dissociate because hydrogen fluoride is the world's fluorine is the world's most electronegative element, so it will hold on to hydrogen and will not allow HF bond to separate or dissociate, and if that does not dissociate, the reaction does not proceed. So what are we going to do is we quickly going to combine H and OH to form H2O, and Br will get attached over here. We are going to get what? We are going to get an haloalkane. That's what we are desired for, a preparation of haloalkane, and we have prepared an haloalkane. Which haloalkane have we prepared? We have prepared bromoethane, also called as ethyl bromide in common names. This is IUPAC name, bromoethane. Okay, so you can use any of the hydrogen halides. The next is Darjan's process by using SOCl2. So again, I would pick up the standard alcohol, ethanol. This ethanol is also used in beverages. It's also used as a cleansing agent, sterilizing agent, as a solvent. So these are the different uses of this alcohol. Well, so I'm going to use thionyl chloride. Thionyl chloride is SOCl2, but I would prefer writing SOCl2 in this fashion so that you understand. S double bond O, Cl and Cl. So what's going to happen is H and Cl is going to combine to form HCl over here, and this SO and O will combine to form SO2 over here, and remaining Cl and this CH3 CH2 will get attached to form chloroethane this time. So this is the commercial method for the manufacture of chloroethane. Why is it the commercial method? Because if you observe, the byproducts are gases which can be easily separated, and we can easily get our product chloroethane. Okay, so chloroethane is prepared by the commercial method called as the Darjan's process. This particular process is called as the Darjan's process. Okay, this particular process is called as the Darjan's process. It's the commercial method for preparation of haloalkanes. Then we are going to use PCl3. Now let's talk about PCl3. In PCl3, again, I'm going to take our standard alcohol, ethanol, and while using PCl3, I will be requiring 3 moles of alcohols. So can't you simply write 3 like this? Yes, I can write simply 3 like that, but I need to explain something in detail. That's why I'm using 3 times ethanol. Okay, so here we are having PCl3. Okay, so what's going to happen is, have a look over here. 3 hydrogens, 3 oxygens, and 1 phosphorus is going to combine to form H3PO3. 3 hydrogens, you can see H1, H2, H3, phosphorus, and then 3 oxygens, that is H3PO3. So what acid which you have got over here is phosphorus acid. What's the name of this acid? It's phosphorus acid. Okay, and to your surprise, it's a dibasic acid. Okay, see, have a look over here. HCl is a monobasic acid because it gives H1H plus ion. Okay, sulfuric acid is a dibasic acid because it gives 2H plus ion. Now you must be wondering that H3PO3 will be a tribasic acid, but it is not a tribasic acid, rather it is a dibasic acid. So then who's a tribasic acid? Phosphoric acid, not phosphorus. Phosphoric acid is a tribasic acid. Why is it a tribasic acid? Because if you look at the structure, you'll understand. This is also asked as a give reason in your exams, that why phosphoric acid is tribasic and why phosphorus acid is dibasic. So have a look over here. This is the structure of phosphorus acid. So you can check out over here that these 2 hydrogens are connected to oxygen, so they get polarized. Oxygen will pull electrons from hydrogens and it will polarize them, kick them out, and give away 2H plus ions. But this hydrogen cannot be donated because it is not attached to oxygen, it will not get polarized. And that's the reason why this hydrogen cannot be donated. Hence, this phosphorus acid, which is H1, H2, H3, PO1, O2, O3, H3PO3, is a dibasic acid. Whereas, on the contrary, if you have a look at phosphoric acid, so phosphoric acid, all the 3 hydrogens are connected to oxygens, and because all the 3 hydrogens are connected to oxygens, all the 3 hydrogens can be donated, and that's the reason why this is a tribasic acid. All the 3 hydrogens, oxygens get polarized, and it's a tribasic acid. It's not a dibasic acid. Okay, so this one is tribasic, this one is dibasic. You can explain it using the structure. Okay, so coming back to the reaction, we formed H3PO3, that's phosphorus acid. We have 3Cl remaining, 3 ethyl groups remaining. Now I need not write 3 times. I can simply write 3CH3CH2Cl. That's what? Chloroethane. What is this? Chloroethane. Okay, so this is what we have prepared using alcohol and PCl3. Which haloalkane we have prepared? Chloroethane. Now it's time to use PCl5, the next method. Okay, we're going to use PCl5 again with alcohol, converting alcohol to haloalkane by using what? PCl5. This time no need to take 3 times or 5 times. What are we going to do is we are going to combine P oxygen and 3Cl. If you're not understanding, have a look over here. We'll write PCl5 in this format: 1, 2, 3, 4 and 5. So we are going to combine this PO, these 3Cl, P and oxygen. So this forms phosphorus oxychloride. What has it formed? Phosphorus oxychloride. Now one Cl will combine with H to form HCl, and another Cl will combine with CH3CH2 to form chloroethane. So what do we get? Chloroethane. We're going to get chloroethane. Okay, so this is one way of forming chloroethane haloalkanes from alcohols. 4 methods in which we have converted alcohols to haloalkane. Now all these methods starting from alcohol to haloalkane are over. Now we are starting with the next preparation method, which will be the next preparation method, that is, we'll prepare it from alkenes, right? We'll be using what? Alkenes to convert or to prepare haloalkane, right? We're going to convert alkene into a haloalkane. So it's an alkene. There are 2 types of alkene. One is a symmetrical alkene and the other one is an asymmetrical alkene. So why is this symmetrical? This is symmetrical because both the carbons are having equal number of hydrogens, and because they are having equal number of hydrogens, we can easily add, say for example, Br2. If you want a geminal dihalide, okay, like if you want to form a geminal dihalide, you will add Br2. You'll get 1 Br over here, 1 Br over here. So this is a geminal dihalide. Geminal dihalide is the category I've explained in detail during the classification of haloalkanes in part 1. If you have not yet seen that, you can go back to the first video, part 1, and see what is a geminal dihalide. Then I've also explained what's a vicinal dihalide. Vicinal dihalide you get when you are having both the halogens attached to the same carbon. Here 2 halogens are attached to two adjacent carbons, but in vicinal dihalide, two halogens will be attached to the same carbon. Okay, so this is a geminal dihalide. We can call it as 1,2-dibromoethane. Okay, 1,2-dibromoethane will be the IUPAC name. Here you can, if you want a monohaloalkane, you can use HX or you can use HBr. So H plus and Br minus. To any carbon we can attach the positive and negative part, so that we get what, because it's a symmetrical alkene, it does not really matter where you are attaching the positive part, that is hydrogen, and the negative part, that is Br. In both the cases you are going to get one bromo ethane. Even if you do vice versa, aisa vaisa, right? If you attach hydrogen over here, attach bromine over here, still the product is going to be one bromo ethane. Okay, so wherever you attach, it does not matter for symmetrical alkanes, but for asymmetrical alkanes it does matter. What is asymmetrical alkanes? The two carbons which are having the double bond, you can see that the two carbons which are having the double bond have unequal number of hydrogens, and hence it is asymmetrical. And to such a case, when I add a positive and negative, that is HX, positive part is hydrogen, negative part is the bromide. Okay, so here we have to follow a rule. What is the rule? The rule says that the negative part should get attached to the carbon having least number of hydrogens. What does it say? The negative part should get attached to the carbon having the least number of hydrogens, and the positive part should get attached to carbon having more number of hydrogens. So here we'll be getting CH3 single bond CH, double bond CH, sorry, not double bond, this time we'll get single bond CH2. I'm just copy pasting, and here you're going to get attached the Br, and that's the negative part, and here the positive part, that is the hydrogen. So this becomes 2-bromopropane. What does it become? 2-bromopropane, which is 80% of the product. This is according to Markovnikov's rule. What is this rule called as? It's called as Markovnikov's rule. What does the Markovnikov's rule say? It says that Markovnikov's rule. It says that the negative part should get attached to carbon having least number of hydrogens, and the positive part should get attached to carbon having the most number of hydrogens. Now you must be thinking that, sir, this is having even more number of hydrogens, but it is not sharing a double bond, right? So we will not involve this carbon into the reaction. Okay, so you will not attach anything to this carbon because it's saturated. Although it's having more number of hydrogens, it's not attached to the double bond, so it's not associated with this. In addition reactions, we only consider the two this is an addition reaction, by the way. Okay, so addition reaction, we only consider the two carbons which are involving with the double bond. The remaining carbons will be copy pasted. Okay, so all addition reactions obviously convert double bond into a single bond. Okay, or a triple bond into double bond. The number of multiple bonds decrease in what? Addition reactions. So this is the 80% of the product. दिखना कि 80% rule है, Markovnikov's rule है, तो 80% molecules follow the rule. Just like traffic signal है, traffic signal पर red light लगता है, 80% people follow the rule, they stop. But 20% people इधर उधर देखते हैं, and if there is no traffic police, they try to escape. So 20% people are breaking the rule, 80% people are following the rule. Similarly, 80% of the molecules are following the Markovnikov's rule, and 20% of the molecules will disobey Markovnikov's rule, and in that, here the positive part will get attached to the carbon having least number of hydrogens, and the negative part will get attached to carbon having more number of hydrogens, resulting in one bromopropane. Okay, one bromopropane. Here you got two bromopropane, here you are getting one bromopropane. Okay, and that's just the 20% of the product. So 80-20 rule for Markovnikov's. Similarly, we are also having something called as anti-Markovnikov's rule. In anti-Markovnikov's rule, what's going to happen? Anti-Markovnikov's rule can only take place in the combination of HBr and peroxide. Only if and only if I use HBr, and along with that, if I use a peroxide, say for example Na2O2, okay, or H2O2, any peroxide. So only in the combination of HBr and peroxide, anti-Markovnikov's rule will be followed. Anti-Markovnikov's rule, by the way, is also called as Kharash-Mayo effect. Okay, also called as Kharash-Mayo effect, also called as peroxide effect. Okay, so there are different names of this anti-Markovnikov's rule, Kharash-Mayo or the peroxide effect. So it takes place only in the presence of a peroxide and HBr. If any of the two are absent, this anti-Markovnikov's rule will convert into Markovnikov's. It will not be followed. Anti-Markovnikov's rule will not be followed. Okay, when if there is, instead of peroxide, if peroxide is not there, HBr is there, no use. Anti-Markovnikov's rule will not be followed. If HBr is there, peroxide is there, and instead of HBr we are using HCl, HI, HF. That won't work. Okay, there is some dissociation enthalpy, and because of that, the HBr is only required. HCl, HI, and HF will not give you anti-Markovnikov's rule. So if you want anti-Markovnikov's rule to happen, you have to use HBr and peroxide in combination together. If you use one of them and not the other, then anti-Markovnikov's rule is not going to take place. Okay, so what's going to happen in anti-Markovnikov's rule? What was 80% will become 20%, and what was 20% will become 80%. That means, according to anti-Markovnikov's rule, the negative part should get attached to the carbon having more number of hydrogens, and the positive part will get attached to the carbons having least number of hydrogens. So when this happens, you get one bromopropane as your major product according to anti-Markovnikov's rule, that is 80%. And 20% people break the anti-Markovnikov's rule also, 20% of the molecules, and hence you get 2 bromopropane as the minor product. So this is the anti-Markovnikov's rule. Markovnikov's and anti-Markovnikov's, both things we have done. From alkenes we have converted it into haloalkanes. Now another method of preparing haloalkanes would be by halogen exchange. We are preparing it by what? Halogen exchange. Now what is halogen exchange? Already it's a haloalkane. You just have to exchange the halogens. Now the first reaction which we are taking is Swartz reaction. Now I've just changed the spelling a little. Instead of SWARTS, I'm using SWARFs, SWARFS. So why are you doing so? Because we need to remember something. You can remember S for silver or A for Ag and F for fluoride. So you need to remember that in this reaction you have to use a compound, a reactant called as silver fluoride. So here you can use any haloalkane. Say for example bromoethane I'm taking. You can take any haloalkane but not fluoroalkane. So for the first time we are preparing a fluoroalkane. Okay, AgF. So what's going to happen? Ag is going to combine with Br to form AgBr, and F is going to get attached in place of the halogen. That is, I call this as iski topi uske sar. Iski topi uske sar meaning what? This halogen is being given to this and his halogen is being given to this. So that's why I call it as halogen exchange or iski topi uske sar. We are just exchanging the haloalkanes. Okay, so this is Schwartz reaction. Then we are having Finkelstein reaction. Now in Finkelstein, check how to remember that Finkelstein. I'm going to write the last two letters, capital I and N. N will stand for Na, I will stand for iodine. Basically one of the reactants has to be sodium iodide. So we are going to use CH3CH2 Cl this time, and NaI. You can use any haloalkane over here except for iodalkane. Sir, अगर आप iodalkane use करते हो तो क्या होगा? If you use iodalkane over here also there is iodine. What is the point in exchanging? You won't get any new product, and there will be no chemical reaction. So here for a chemical reaction to occur, you have to use a separate haloalkane over here. Okay, you have to use a separate haloalkane over here. So CH3CH2Cl. So here you will get NaCl plus CH3CH2I. That is nothing but iodoethane. What it is? Iodoethane. So this is a way to prepare what? Haloalkanes. Another way to prepare haloalkanes. Now moving to the last part of preparation of haloalkanes, that is, see, we have done from alcohols, we have done from exchange, halogen exchange, we have done from alkenes. Now last part is halogenation of alkanes. Like halogenation of alkanes is simply you take an alkane, add Cl2. This reaction you have done in your 10th standard as well as in your 11th standard. So what do you do over here? This chlorine is free radical mechanism. This chlorine will split into chlorine free radicals with the help of UV light or with the help of diffused sunlight. Okay, so either we'll use what? UV light or diffused sunlight. Because of this, what will happen? This chlorine will break into chlorine free radicals. Now when it breaks into chlorine free radicals, obviously free radicals are with the unpaired electrons. Free radicals are atoms with the unpaired electrons, and they are highly reactive. So what are they going to do is they are going to attack this methane molecule, and you can see that the methane molecule is having covalent bonds between carbon and hydrogen. So what is this unpaired electron of chlorine going to do? The free radical of chlorine will remove or abstract the hydrogen from there, forming HCl. Resultingly, what's going to happen with the carbon? The carbon will be left with a unpaired electron, and hence carbon is also unstable now, and this chlorine is also with an unpaired electron. So the chlorine will combine over here. Okay, both of them will combine to form CH3Cl, that is chloromethane. Okay, this is chloromethane. And in this particular reaction, what's going to happen is, you've seen the movie Sholay, right? उसमें बसंती बोलती है, गाना गाती है, right? वीरू के लिए. Okay, क्या आज जब तक है जान मैं नाचूंगी. यू मस्ट बी थिंकिंग हाउ डज इट रिलेटेड विद दिस रिएक्शन. इस रिएक्शन में भी ऐसा ही कुछ हो रहा है. इस रिएक्शन में क्या हो रहा है कि जब तक है हाइड्रोजन, वहां पे बसंती बोल रही जब तक है जान मैं नाचूंगी. यहाँ पर ये रिएक्शन बोल रही कि जब तक हाइड्रोजन है, राइट, जब मीथेन बोल रहा है कि जब तक हाइड्रोजन है उसमें, तब तक रिएक्शन होते रहेगा. ठीक है, रिएक्शन रुकेगा नहीं. ठीक है. So here you are getting CH3Cl. Okay, now this CH3Cl, one hydrogen has been removed, will further be treated with chlorine, and with the same mechanism, diffuse sunlight. See, if you use direct sunlight, it's going to explode. Okay, so you have to use diffuse sunlight. You cannot use direct sunlight, or you cannot perform the reaction in dark. If in dark, the Cl2 will just not dissociate, and this is in particular homolytic dissociation. Okay, in particular, it is homolytic dissociation. So when what's going to happen? One more hydrogen will be removed, HCl. You're going to get CH2Cl2, and this is going to continue. One hydrogen will be removed, one Cl will be attached. So hydrogen will keep on getting replaced with Cl, or you can say hydrogen will be substituted by Cl, because it's a substitution reaction. So we'll get CH2Cl2, CHCl3, and finally we'll get CCl4. So this is chloromethane, this is dichloromethane. Okay, and this is trichloromethane, also called as chloroform. Okay, or methine trichloride. Trichloromethane, I'm writing the IUPAC name. Common names I'm telling you orally. This is chloromethane IUPAC methyl chloride, dichloromethane IUPAC or methylene dichloride, common name. Trichloromethane is IUPAC, chloroform is common, and one more common name, methine trichloride. And tetrachloromethane is the IUPAC, and carbon tetrachloride is the common name. Okay, so here what are we going to get? Same thing, no? CH2Cl2 plus Cl2. Here you will write CHCl3 plus Cl2. It's a very simple reaction, very basic reaction. That's why I'm doing it a little fast, because you have done this in your 10th and 11th standard. It's very easy. Okay, so you can see that continuously one hydrogen is going on getting reduced. There were 4 hydrogens over here. There are 3 hydrogens over here, 2 over here, 1 over here, and ultimately none over here. Okay, so this is how you are converting alkanes to haloalkanes, but this method we don't prefer. Okay, why we don't prefer? Because we get a mixture of haloalkanes. You cannot actually stop this reaction at the first step or second step. It will go on continuing. So it is uncontrolled kind of reaction. That's why we get a mixture of products, mixture of haloalkanes, and hence we do not use this, or do not prefer using this particular reaction, which is called as halogenation of alkanes. So 4 methods of preparation are given in your syllabus, and we have completed that. Let's meet you in the third part of haloalkanes, where we are going to discuss about the chemical properties of haloalkanes, SN1 and SN2, mechanism of haloalkanes. Thank you.